Hey everybody, welcome to our SAT office hour tonight. Our topic is going to be geometry. But before that, let's go over our challenge problems for the week. And we have some pretty difficult ones, I believe, here. So for number one, we've got some function here that's factored in one way, and then it also can be factored another way. And it wants us to find the value of n. Now it's telling us that this information, there are two distinct values such that g of x is equal to 0. Well, this one is going to produce one of those values. It would just be at negative a, all right? So what that information is telling us is that this only has one solution, or 0, or root, or factor, however you want to look at that. And when that happens, when they talk about the types of solutions to a quadratic, we want to think of the discriminant. That's the b squared minus 4ac. And whenever you have one solution, that is going to equal 0. That is the part of the quadratic formula that's under the square root. And if you have a 0 there, then the plus or minus in front of it's going to be plus or minus 0. So you're just going to get one answer because of that. Now, in this equation, b squared, b is b, and c is c, and a is 1. So b squared minus 4c is equal to 0. And then we're just going to put that on hold for a second. All right, so that's what that information tells me. And then the other thing is I know these two are equal to each other. So I know that x squared plus bx plus c is equal to, so also notice that there's an x plus a here, so I can kind of just ignore them. So this part has to be equal to this part. Now I'm going to distribute the 1 over m, because then that's going to give me x squared plus bx plus b squared over m. Okay? So I've just set some things equal to each other. I've used a discriminant. Now I look and I say, all right, well, x squared is x squared. That doesn't really matter. Bx is bx, so that doesn't really matter. But here's the key. C would have to equal b squared over m. And our goal is to find m. But I've also got this, which tells me that b squared is equal to 4c. Well, now I'm getting somewhere because if I replace this, if I've got c equals b squared over m, then c equals 4c over m, multiply by m, mc equals 4c. Well, then I can cancel the c's, and m would have to equal 4. And there you go. So that's a really hard problem, in my opinion. But once you see the solution, it doesn't look that hard. That's how all hard problems are, right? So the idea is figuring out ways to get started and having these cues, these things like my brain sees the type of solution to a quadratic, I'm automatically going for the discriminant. Then when I can't really do much with that, I look for something else to do, which is set things equal, distribute, match terms. So there's all kinds of things you can do to kind of keep moving yourself forward and then eventually finding a way to use some earlier information. All right, let's move on to number two. All right, so we got another difficult one here. A parabola has a vertex of 3, -10, and then it can be written, it intersects at 2 points. So what that tells me is that 3, -10 is down here. For it to intersect at 2 points, it has to be the type of parabola that opens upward. And that means that a is greater than 0. So again, that's what that is telling me. Now I'm going to put that on hold. If they give me a vertex, I'm going to start to come up with the equation in vertex form. So that's a times x minus h squared plus k, which is y equals a times x minus 3 squared minus 10. All right, so again, the vertex is h comma k, and I just plug it into vertex form. Now, in order to get it into standard form, I just need to multiply out a little bit. So we should hopefully know that x minus 3 squared is x squared minus 6x plus 9. And then finally, I distribute through the a. So ax squared minus 6ax plus 9a minus 10. Now they want a plus b plus c. Well, A is A, B is negative 6A, right? B is the coefficient of X. C is the constant. That's 9A minus 10. So they want us to be to add A, B, and C. So again, A is A, B was the coefficient of X, and C was the constant out here. Now, if I simplify that, that is 4A minus 10. Now, remember this in the very beginning. A has to be positive for this to intersect the x-axis twice with this particular vertex. Well, it says which could be a value of A plus B plus C. Well, what ends up happening is let's say I make it equal to negative 6, the first answer choice. Well, if I add 10 over, I'm going to get 4, so I will get a positive A. Once I start trying the other ones, negative 10, add 10 over, I'm going to get 0. Negative 12, add 10 over, I'm going to get a negative. Negative 14, add 10 over, I'm going to get a negative. So negative 6 is the only one that when I set 4a minus 10 equal to will give me an a value that is positive. All the others will give negative a values, so they can't work because it would contradict what we talked about in the very beginning of the problem. Again, really hard problem, really high level problem, but this is an example where they can make questions really hard where Desmos is not that helpful, and you've got to really know the concepts. You got to know vertex form, how to get it into standard form. You have to understand without Desmos that how graphs work, where the vertex work, where whether A is positive or negative. So like those concepts are really important to marry those with Desmos to kind of give you the best possible chance here. Okay, so now on to our problems for the night. And these are all going to be related to different geometry concepts. And one important geometry concept is the idea of scale factors. So here in number one, we got two similar cone-shaped silos, A and B. They have corresponding heights in ratio 1 to 3. So we would call that, I would say that that is our scale factor. I'm going to call our scale factor K. So this means K equals 3. And what that means is any single dimension, I'm going to call this our 1D scale factor. Any single dimension, whether it be height, radius, length, width, perimeter, in this, to go from the smaller one to the bigger one, we're going to multiply by 3. That's what this is telling me. Okay. Now, if I want to jump to volume, which is a 3D, okay, that is going to what we're going to multiply by is not the scale factor anymore. We're going to multiply by the scale factor cubed because we're now in 3 dimensions. So volume is really our only example of something in 3 dimensions. So anytime you're doing the volume, you're multiplying by the scale factor cubed. Well, 3 cubed is 27. So since we're multiplying by 27, silo A is the smaller one. So that's 150 times 27 is going to give you 4,050. That is a 0. All right, so these problems, we could kind of choose values and all, but that gets way into too much. So when they're talking about similar figures, we're going to use the idea of scale factors. And might as well mention it here. If they talked about area, we would have used k squared as our kind of multiplier. And any single dimension k, any area or surface area k squared, any volume use k cubed. Okay, so now we look at another one. So moving on to number 2, we look at another one. So the area is 576 times the area of square B. So that means the area is 2-dimensional. So that's really k squared. That's equal to 576. Well, perimeter is a 1D concept. Well, 1D is always the scale factor itself. So all we have to do is square root this, and that ends up being 24. So the perimeter of square A is going to be 24 times the perimeter of square B. So again, all we're doing is using scale factors here. The scale factor K represents any single dimension, which perimeter falls into that. Anything area is K squared, and anything volume is K cubed. All right, that's it for that one. All right, moving on. So we kind of change pace here and we go to a hexagon. So here is what I want you to think when you see a hexagon. Anytime you see a hexagon on an SAT, I want your brain to automatically go 30, 60, 90. Why 30, 60, 90, you ask? Because when I have a triangle, these triangles in a hexagon, this particular one, this right triangle here, if you imagine me making these triangles throughout, hopefully without me drawing them, you can see that there's going to be 12 of these, right? Two per side. Hexagon has six sides. Well, if there's 12 triangles, if I want to find this angle here, if those 12 angles are going to make a full circle, that's going to be 360. And 360 divided by 12 is uh, 30. So when you have a hexagon, you are going to have 30, 60, 90 triangles. That's the idea. And AB is this. So I'm just kind of making this a little bigger here. And AB is 20. So now we've got to use the ratio. So if you look up the ratios on your reference sheet, we know that a 30, 60, 90 is going to be X is the short leg, the long leg is X root 3, and the hypotenuse is 2X. Well, if 2X is 20, then that means X is 10. So that means my sides of my right triangle are 10 and then 10 root 3. And then if we want the area of this triangle, remember the area is 1/2 base times height, which is 1/2 10 times 10 root 3, which is 150 root 3. All right, so again, see a hexagon, automatically know that you're going to be using 30, 60, 90 triangles. Okay, on to number 4. Um, BC and DE are parallel. AD is 6. All right, what is the length of BC? So we're going to call BC X. All right. So there's a couple things here. Since these are parallel, if this is a right angle, then this is a right angle. They are called corresponding angles. They also share this angle, or this angle here has to be congruent to this angle because they're also corresponding. And once you have two angles that are the same, you have what are called similar triangles. So these triangles are going to be in proportion with each other. But what I first want to do is I want to find DE. Well, hopefully we remember our Pythagorean triples. One common Pythagorean triple is 3, 4, 5. This is a multiple of 3, 4, 5. If you double that, you get 6, 8, 10. And so if I have 6 and 10 here, that means this is 8. So that's the first thing. You want to avoid having to use the Pythagorean theorem if you just know your triples. I would say 3, 4, 5, and 5, 12, 13 are the most important to know. So then we set up a proportion because this triangle is similar to the big triangle. So 8 over x, this is where we have to be important, or important. We have to be careful. We are going to do 8 over x, and then that's 6 over, not 9, the whole length of the triangle, all right, which is 15. I get that by doing 6 plus 9. Now I have a pretty easy problem. I can just cross multiply. I guess that means a couple different ways you could do it. So I could just do 6x equals 15 times 8 is 120. So if I divide by 6, x is 20. And the length of segment BC, that's what they asked for. That's what we called x. So the answer would be 20. So we've got similar triangles there, and then we also have Pythagorean triples. Okay, moving on to number 5, testing some just like angles and isosceles triangles things going on here. So AB and AC are the same, and AD and CD are the same. So the first thing I would do probably is if I want to make my way over to X, just start filling stuff out. So I'll start with 115. If that's 115, then this angle here has to make a linear pair. So I subtract from 180 and I get 65 degrees. Okay. Now I have an isosceles triangle. If this side is equal to this side or it's congruent, then these base angles are the same. So if these are both 65, then I know the angles of a triangle add up to 180, and 65 plus 65 is 130. So I have 50 left over for this. And then if I look along this straight line, I have a 50 and a 90. Together, that's 140, which means this angle here is the other 40. So again, these three angles along the straight line or the straight angle have to add up to 180. Now, lastly, if that's 40, I have another isosceles triangle. So this is 40. And then this triangle, 40 and 40 is 80. So the x that's left over must be 100 to bring me back to 180. All right, so we've got linear pairs are supplementary. We've got the three angles of a triangle add up to 180. Isosceles triangles have two congruent sides and two base angles are congruent. And we've also got, when we have three angles on a straight angle, they add up to 180. And this symbol means 90 degrees. All right, so just a quick review of a bunch of different angles that you could have to put together here in one problem. All right, moving on to number 6. So we've got this setup. This is a very specific setup. We've got three right triangles here. I'm going to think of them as the small right triangle right here, the medium right triangle, and then the overall big right triangle. So there are three of them. Whenever you have this setup where you have like two right triangles that make up a bigger right triangle, all three triangles are similar to each other. These are called similar right triangles. So we're going to treat them that way. We're going to try to set up a proportion. So what is the length of DB? I'm going to call that X. And then what I can do is, I'm not sure, I think what I need is this whole length BC. And I can get that by a quick, again, 3, 4, 5 triangle. Try to avoid the Pythagorean theorem if possible, because there's usually a quicker way. So this is just multiplied by 5, right? 3 times 5 is 15, 4 times 5 is 20, and 5 times 5 is 25. So immediately I know that this is 25. And then the way that I'm going to do this is I'm going to first look at the small triangle and make a relationship. I'm just going to go x over 15. And what x represents is the short leg. And 15 represents the hypotenuse. So what I want to do is I want to go to another triangle. I'm going to go to the big triangle. And I'm going to make the same relationship. I'm going to make the short leg, which of the big triangle is actually 15, over the hypotenuse, which we just found to be 25. So that's how we're going to solve this. So we do just, again, easy cross multiplying. 15 times 15 is 225 equals 25x, and 225 divided by 25 is 9. So the length of DB is 9. All right, moving on to number 7. This one's pretty tough. So in the right triangle ABC, BC is 25. AC is 12. If the ratio of AD to DB is 3 to 2, what is the area of triangle BCD? Um, okay. So here's how I'm gonna do this one. This one's pretty tough. So the ratio of AD to DB is 3 to 2. I'm gonna think of that as 3x to 2x. I think that'll make sense in a second. Okay. Um, or you know what? I'm gonna do this. I don't think I'm gonna use x. I'm just gonna go straight to what I'm looking for. I want the area of triangle BCD. which I have the base. So remember, area is 1/2 base times height. So that's 1/2 25. Whoops, it's a weird 25. 25 times the height. Well, the height is this. So what I want to notice is I want this. So look at this triangle. And then I want to compare that to this triangle. What I'm making right now are similar triangles. All right. And so the thing that I'm looking for is this. This is what I'm going to call H. That is the height that's going to go here. Well, the height goes with this 12. So H over 12 equals. Now, here's the important part. I want BD to BA. Well, I know BD to AD, or sorry, AD to BD is 3 to 2, right? But I want BD to the whole thing. So if this one is like 3 to 2, well, the whole thing is like 5. So I know they're not the actual lengths, but they're just the ratios. So if I want the ratio of DB to the whole thing, that's 2 to 5. This is how I'm going to find H. So again, simple cross multiplying. 5H is 24. So H is 24 over 5. So I'm going to put 24 over 5 here. You could just multiply all this out in a calculator. You could do some simplifying, like this is 5 and this is 12, and then you'll get your 60. But you have a calculator, so you can just throw it all in there. All right, so again, that's a pretty hard one to know that you got to find this height and then finding those similar triangles and making the ratio 2 to 3 to really 2 to 5. That's what you wanted, was the full thing. So that's a pretty tough problem. All right, number 8. Okay, so here's one where we have that scenario with the 3 triangles, but we're not going to do that in the same way. But we're going to use the idea that they are similar triangles. So we want the value of sine A. So the thing that we want to realize is that all of the triangles are similar to each other. So we are going to use that fact. Well, A is the side that's opposite, or sorry, it's the angle that's opposite the short leg. So if I go to this little triangle, the side opposite the short leg is this angle. That means those angles are the same. Because remember, similar triangles are just all the angles are the same. Or you could look at it as this is clearly the right angle. Angle B is angle B. So this is the other angle. This must be the same as angle A. Now I'm just going to find the sine of this angle. Well, the sine is the opposite, which is this one, over the hypotenuse. Well, we don't know the hypotenuse, but again, remember your 3, 4, 5s, all right? So if I multiply by 3, that's 9, 12, 15. So that's just 15. So the sine of A is 9 over 15, which then just reduces to 3 over 5. So it really could have just realized it was a 3, 4, 5 and just done 3 over 5 because it was going to reduce anyway. Okay, moving on to number 9. So in number 9, we are going to go to some circles combined with triangles. So in this above, what is the area of triangle OPQ? So here's the deal. We know that if this is 8, then this is 8 because they are both radii of the same circle. And then if these, now we have at the very least an isosceles triangle because this is 8 and this is 8, which means these base angles are equal. Well, if they all add up to 180 and 60 is here, then that's 120 is split up between these two. So they're each 60. So it's not isosceles, it's actually equilateral. Here's another one. When you have an equilateral triangle, again, you want to think of 30, 60, 90. Because if this is 60, if I drop an altitude, now I have a 30, 60, 90 over here. And I'm going to make another, I'm going to draw it over here just so you can see. So this is Q, this is whatever point I drop the altitude, and this is O. All right, so this is 60, which means this would be 30, and this is our 90. And if this whole thing is 8, then this piece is going to be 4. I already know this is 8, and then this is just 4 root 3 using my ratios. And then I want the area of OPQ. So I actually want the area of the whole thing. So what I have is area equals 1/2. The full base is 8, and the height we just figured out is this, 4 root 3. So that ends up being 16 root 3. All right, so we talked earlier about hexagons. So anytime you have hexagons or equilateral triangles, you immediately should be thinking 30, 60, 90. Okay, number 10, we got equation of a circle. So the way an equation of a circle works is it's x minus h squared plus y minus k squared equals r squared, where h and k is the center and r is the radius. Well, we want the radius for this problem, but let's just go over all the concepts. So we've got x squared plus 2x. Then I'm going to leave a space. And then I've got y squared minus 8y. I'm going to leave a space. And then I've got equal to 64. So what we're going to do is we are going to complete the square. I want to make a perfect square. The way I make a perfect square is I make sure that a is 1, and it is. Then I take half of b and I square it. So half of 2 is 1, 1 squared is 1. So I'm going to add 1. And if I add 1 to the left side, I got to add 1 to the right side. Now over here, half of b is -4. -4 squared is 16. So I'm going to add 16 to one side and 16 to the other. So what that represents is this is now x plus 1 squared. And this, if you factor it, is y minus 4 squared. And over here, I get 81. Well, that tells me that I can find my center, but I just need the radius. So this 81 represents r squared, so the radius is 9. If you had to, for a different problem, the center, h would be -1 and k would be +4. So they're the opposite of what you're looking at, because if h is -1, minus a negative is going to turn it to a plus. And if k is +4, you'll actually still see the minus once you plug in a +4. But on a problem like this, when you get really good at these, you kind of ignore the left side. If we want the radius, just focus on the right side. Add your two completing the square values, and boom, you've got the radius squared. Okay, on to number 11. So in the circle above, AOB is a central angle. The minor arc AB is 2 pi, and the radius is 5. What is the value of angle AOB? So I'm going to call that x in degrees. So if you look up on your formula sheet, you're going to see that the circumference of a circle all the way around the circle is 2 pi r. Well, if I want the arc length, I don't know, let's say L. L is the length from here to here. If I want that, that's going to be x, whatever the central angle is, over 360 times 2 pi r. It's just going to be a fraction of going all the way around. And all the way around is the circumference. So then I just substitute in. L is 2 pi, x is what I'm looking for, and r is 5. Well, 2 pi cancels with 2 pi, and I could divide by 5. So there's like a 1 here, so I get 1/5 equals x over 360. You could cross multiply. 360 equals 5x, and divide by 5, and you get x is 72. All right, which should make sense, because if the radius is 5, the circumference is 10 pi, and this 2 pi is 1/5 of that. So this angle should be 1/5 of going all the way around. All the way around is 360, and 1/5 of 360 is 72. All right, on to our last problem. So we're back to the equation of a circle, and we want to know the coordinates of the center of the circle. So what we're going to do is we're going to try to rearrange this a little bit. And at the same time, actually, the first thing I'm going to do is I'm going to divide everything by 4. So I'm going to get x squared plus 5ax plus y squared equals 3/4 c plus 7by. Then I'm going to do everything to one side, kind of. So I'm going to do x squared plus 5ax, leave a space, then y squared minus 7by, and leave a space, and then equals 3/4 c. Okay, so now here's the important thing. I'm going to jump back real quick. We could complete the square, but we don't really need to because then that we'll be adding that to the other side. It'll help us find the radius, but we only want the center of the circle. So I want to jump back to number 10, and I want us to look real quick at what we did here. So after we figured out what we completed the square, we turned it into a perfect square. So notice the perfect square was matched the plus, and then half of that number was there. So it was x plus half of b squared. And then over here, the minus carried through, and it was y minus half of b squared. And then it was that allowed us to figure out the center of the circle. So let's go back to this one. Without actually completing the square, I know that I'm going to end up with an x plus half of 5a. So 5a over 2 squared. And then I'm going to have one here. This is going to end up being y minus half of 7b squared. Again, if I actually squared them, that's what I would add here, and I would add that to this side, and that would allow me to find the radius. But I don't need the radius in this problem. I just need the center of the circle. So I figured out what my factors are going to be. So that means my center is going to be essentially the opposite of these. So 5a over 2 comma 7, negative 5a over 2 comma 7b over 2, which is just c. All right, and the reason that is because when h is negative, remember the formula is x minus h squared plus y minus k squared equals r squared. So when you plug in a negative for h, the double negative is what turns it positive. And when you plug in a positive for k, the negative still is there. That's why when we get the center from it, we're kind of looking at it the opposite of what our brain sees. Okay. Well, thank you for watching and attending. Please, I'll splice these up individually for TikTok. Check out TikTok for our other stuff, all the other material we put out for the SAT. As we approach the March SAT currently, and then May and June coming up here in 2025. We do offer tutoring. Call or text us if you want any like extra help other than this kind of free stuff that we're putting out. All right, thanks again, and see you next week.